degree at Frankfurt in 2009 and became a junior faculty in 2012. And in 2018, Tetyana received her tenure at Darmstadt. Since 2018, Tetyana has been group leader for the QCD matter research in the department HADES at the GSI. And Tetyana has been leading quite a lot of direction at HADES. And I think she's a well-known expert in the Dilepton field, in the thermal radiation and EM radiation, all those kind of things. So Tetyana, the floor is yours. And
yes, thank you.
Of course, yeah, Tetyana is going to talk about HADES results.
Yes, thank you very much, Lishwan, for very kind words and introduction. Yes, it's also a pleasure to be here with you today and to share with you some of our more recent, some less recent results, results from HADES, but I will try to put them all in the context of what we have learned so far from the experiments that we perform with HADES until recent. So I will give you an overview of our HADES results, and here you see already our experiment. Photo is taken in year 2022, just before the last beam time, and you see many new detectors in the setup, and I will discuss about them a little bit later in the talk. So I know that here just some experts in the audience, but to set the stage, let me just mention that, of course, we are all interested in study the QCD phase structure, which we represent in the planes of temperature and baryon chemical potential or densities. And we do have quite a good guidance from the lattice QCD calculation at vanishing chemical potentials and high temperatures. Lattice QCD predict the crossover between the quark-gluon plasma phase to the hadronic phase. And what we know now with quite a good precision is the position of the so-called pseudo-critical temperature, which is at values of 156 MeV with, as I said, quite a good precision. And this temperature is calculated for the physical quark masses. So what we also know from the lattice QCD calculation are the positions of the true critical endpoint. However, still in the chiral limit, the numbers are 132 MeV, and in the recent work from the hot QCD collaboration, it has been also pointed out that this temperature might be even lower than this 132 MeV. What lattice QCD try to do, they try to extend their calculation also to the finite chemical potential. And here we do have also guidance from lattice QCD that for the baryon chemical potential over TC, smaller than 3, there are no indication for the existence of the critical endpoint. On the side of the high baryon chemical potentials, we know that lattice suffers from the notorious sign problem. There are not the calculations from the lattice QCD available in this regime of on the QCD phase diagram. But we do have also many theories which are guided by the lattice QCD results, and they do predict quite a rich structure on the side of somewhat lower, moderate, and even lower temperatures and high baryon chemical potential. They do predict existence of the first order deconfinement and chiral phase transition. And from here, one could also then conclude that if we have the first order phase transition on the one side and crossover on the other side, there must be also a critical endpoint. And this is what we are after then experimentally, because from both sides, theoretically, but also experimentally, there is quite a large discovery potential in this regime of the QCD phase diagram. The interest to this region on the QCD phase diagram has grown a lot in the recent years. This is also related to the observation 17 of August 2017. As we know, event of two neutron binary and neutron star merge event has been detected in both gravitational but also electromagnetic spectrum. And if one tries to model this event by means of model calculations, here one example of binary neutron star merge event, taking the given equation of state, colliding two neutron stars with the masses of 1.35 solar mass. One can see how does the event proceed as a function of time. On the other side, one can also model heavy ion collisions at few GeV energy regime, for example, by means of microscopic transport models. And here one can also see different time snapshots of the heavy ion reaction. And what one can see from here is that despite 18 orders of magnitude in the scale, in the size of the colliding object, but also in the time of the event itself, if you look at the region of the temperatures and also densities which are enriched in both of events, they are quite similar. And this, of course, provides a very strong connection between the fields and also opens the opportunities to generate the common framework to simulate events like binary neutron star merge event or heavy ion reaction, and also to find the consistencies between the equation of state to describe both events. And here, of course, we can definitely help from either side to get and to understand how does the matter look like when it compressed to the high densities. And this is what is done then in experiments. We do heavy ion collisions at different collision energies, also colliding different system sizes. And we try to extract with as high precision as possible some parameters with which we can contribute to this QCD phase diagram. And some of these parameters are the temperatures and chemical potential at the freeze-out stage of the heavy ion reaction, shown here with the black dots. As you can see, QCD phase diagram has been studied with quite a precision by means of the probes which are produced at the freeze-out, so late stage of the heavy ion reaction, in the quite wide range of the temperatures and baryon-chemical potentials. However, as you can also see, if we go and look to the more rare probes like electromagnetic radiation, there are not so many measurements here, and I show you in this QCD phase diagram temperatures that has been extracted from the dimuon spectra by Na60 collaboration and HADES, and this I will also discuss later in my talk. So HADES aim to study and to understand in details regime on this QCD phase diagram of the moderate temperatures, high baryon chemical potential. HADES focus mainly on the rare and penetrating probes. And there is a very big advantage of the spectrometer because we do have a very strong program to study also baryon-meson couplings, which are absolutely essential to understand the physics of the heavy ion reaction, which is dominated by the excited nucleons or resonances starting from delta, but also going to the higher line baryonic resonances. To do this physics, we do have beams provided by heavy ion synchrotron cis-18, primary proton beams, but also secondary pion beams are available at the GSI facilities. And in combination with the Dilepton spectrometer, availability of the pion beam makes a very unique physics program to the GSI. These measurements with the pion and proton beams we use as reference measurements. So we call them vacuum, or also called nuclear matter effects when the protons or pions collide with the heavy target. And what is also important, we can address electromagnetic structure of baryons, also hyperons, in the time-like region, which is also very little known so far. For the heavy ion collisions, we can collide gold-gold at 2.4 GeV and somewhat lighter system like silver-silver going up to 2.55 GeV in the center of mass energy. And here there are two main points we would like to understand: the microscopic properties of baryon-dominated matter, and also understand what is or establish the equation of state of this matter. For that, we use event-by-event correlations, fluctuations, production of different particles, and also collective effects. And last but not least, we also reconstruct Dilepton spectra to mainly address the microscopic properties of the system. Some basic facts on the HADES. On the left-hand side, you see HADES spectrometer in the expanded view. In the measurement, when measurements are ongoing, HADES is compressed into this yellow frame. So it's really detector sitting close to each other, just 3.5 meter lengths of the detector once it comes to the measurements. HADES is the fixed target experiment, which of course allow us to collect events with the high interaction rates. For the heavy ion collisions, our accepted trigger rate is 8 up to 16 kilohertz, which of course placed or positions HADES in this interaction rate as the function of collision energy quite prominently to the high interaction rate. And in fact, there are many future experiments to come and to measure all these observables with the interaction rates, which is higher to what is now existing to the HADES. But to date, in this range of the collision energies, HADES is the fastest machine which can collect the data. HADES is constructed such that we do not have magnetic field right after the target. So particle identification in the ring, imagine Cherenkov detector happening before the particles are open or deflected in the magnetic field. Our tracking is performed by 2 layers of multi-wire drift chambers, 2 in front of the magnetic field and 2 behind of the magnetic field. Time of flight measurements are then realized with the inner resistive plate chamber detector, and in the outer regions we do have time of flight detector, which are plastic scintillators signal read out by photomultipliers. Since 2019, HADES has installed 5 sectors of the electromagnetic calorimeter, which also opens opportunities to detect real photons. In 2021, we have also instrumented HADES in the inner region with the tracking detectors like straw tubes. This is done in collaboration with colleagues from Panda, and also for the measurement of the time of flight in the forward direction with somewhat reduced precision, but still we do have still forward RPC detector that has been also recently installed. For 2023 and beyond that, we also would like to upgrade our front-end electronics of the multi-wire drift chambers that will allow HADES to reach 100 kilohertz rates. And of course, we look forward to collect also data at this high interaction rates with HADES. One also very important upgrade that HADES conducted in 2019 is related to the performance of our electron identification. So in 2019, together with the CBM colleagues, we have also upgraded RHIC photo camera. We have replaced old cesium iodide photo detection plane by the modern technique of detecting photos with the PMTs. Thanks to this, our efficiency to detect electrons increased substantially up to factor of 6. We also can reach pion suppression factor, which is higher than 10 to the power of 4. It reaches even 10 to the power of 5 in the relevant momentum region. But what is even more essential for the electron pair analysis or Dilepton spectroscopy is the excellent double ring reconstruction. And here on the right-hand side, you can see two rings which are detected in the on the photo detection plane of our RHIC detector. And here, if two electron rings are completely overlapped, just by counting the number of hits on per ring, one could identify also close pairs. But also in the case when the two electron rings are somewhat separated from each other, one could separate and also reject this type of the pairs from the analysis. And to really emphasize on how well the signal to background ratio could be if one involves this type of the conversion rejection is indicated on the bottom right. Here the signal to background ratio as a function of invariant mass distribution is shown for two cases, one without this conversion rejection and one with employing rejection of the close pairs. And you see that we gain a good factor of 5 in the signal to noise ratio, reaching almost 1 at relevant mass region, and also with the very clear signals of the omega, as I will also show you later in the discussion. Event selection and particle identification in HADES is realized by several identification cuts or in different detectors. So first of all, we can use velocity, particle momentum, energy loss in the drift chambers, but also energy loss in the time of flight detector. And as I mentioned, for the electron identification, we use ring imaging Cherenkov detector. Here as an example, I also would like to show you energy loss in the time of flight detector as a function of velocity. And you can nicely see that we can potentially identify particles, light nuclei, and also Z3 particles up to the lithium-6 and lithium-7 that might be, of course, interesting for the upcoming beam times. In the HADES, we use 15-fold segmented targets made out of gold or made out of silver. They have thickness of 25 micrometer and 3.7 millimeter is the length of our target. So why we go with this 15-fold segmented target? Because we would like to still get 1% interaction rate probability, but we would like to reduce the amount of photons that may convert already in the target region. And this is nicely done by this specific target geometry. With our first level trigger, we collect 40 to 50% of the most central collisions, but we also collect minimum bias events on our tape, which are, however, scaled down by factor of 8, but they also serve as an important reference when it comes to the event centrality determination. So here on the left-hand side, you can see observable, which you can build by detecting transverse and longitudinal energy in the spectrometer. Here you see all these 15 targets nicely reconstructed with our software. Then by having this segmented target, but also involving our so-called star detector and also Vito detector, which is placed behind the target, we can also suppress pile-up events, which, as you know, are essential for when it comes to the high-rate fixed target experiments, by almost 5 times 10 to the power of 3, reaching even 10 to the power of 4 reduction of the events with the large number of hits, meaning pile-up events which are not of interest for our analysis. And here you see this determination then of the centrality. For the centrality determination, we use 2 different ways of determining our centrality. One is related to the hits or tracks detected in the HADES spectrometer, but we also can involve information provided by the forward wall detector, which is situated 7 meters downstream the target. And determination of the centrality by using independent detector from the one which measures particles is essential, in particular for the event-by-event fluctuation analysis. Here on the left-hand side, you can see charge distribution measured in the forward wall detector as a function of number of hits measured in the HADES spectrometer. And then one can, by selection of the charge in the forward wall, identify different centralities. You can also use a number of hits detected in the TOF and RPC detector and define centralities by means of the Glauber-Monte Carlo fit to the measured distributions. And this is also done in HADES and discussed in this paper. What is important to mention here is that distributions that we obtained are also in a good agreement with the transport model calculations after they process through the full analysis chain involving digitizers and noise of the detectors. So this gives us also a good confidence on the determination of our centrality in the HADES. For the event plane reconstruction, we again use forward wall detector. Here we look at the hits of charged projectile spectators in the forward wall. Resolution is then determined for sub-events based on the method which is also well known to the community. And by doing that, we can also look at the event plane resolution as a function of the centrality for the different order of the event plane. And you can see that we can reach quite a good precision resolution for the event plane determination. So now, having all this in hand, let me move on and discuss observables, and I will start from the hadron production, but also collectivity of the particles. And I will start from the azimuthal anisotropy, which we determine with respect to the reaction plane in the collision. So we focus on different orders of this azimuthal anisotropy. The well-known V1, so directed flow, tells us about deflection of the matter in the reaction plane. And since long back, it has been also considered as the signal for the first order phase transition. But here I do have a question mark already, because in the more updated model calculation, it seems that this is not any longer the good observable for this type of the physics. Now for the V2, which is the second order of this second Fourier coefficient, one could define like two different regimes in which V2 is smaller than 0 or V2 is larger than 0. And this is all related to the fact with which speed spectators pass the fireball, which also expands. In the case of the small energies, V2 is negative, and it also tells us the spectators pass slower than the fireball expansion, leading to the so-called squeeze out of the system, which is squeezed out because of the presence of the spectators for the long time in the reaction. On the left-hand side, bottom, you can see measurement of dV1 dy at mid rapidity, together with also wall data for these observables. HADES measurement is shown with the red dot, and for V1, but also for V2, you see these characteristic trends, also indicating that we are dealing at these collision energies with the system, with the matter which is squeezed out by the spectators. What we also know from the long back discuss this observable like V1 and V2 are the good observable to constrain equation of state. But this is also usually done by means of the microscopic transport models. And in the more recent papers, one can also find like conclusion from the model calculations that more precise data and more differential data would be essential to get the better constraint on this equation of state. So this is where we try to contribute with our high statistic data. Here you can see measurement of the proton and light nuclei V1, V2, V3, and up to V6. On the left-hand side, these distributions are shown as a function of rapidity. And then one could use parameterization of this rapidity dependence for odd, so V1, V3, V5, but also 2, 4, 6, with the following parameterization, which also allow us then to reconstruct three-dimensional picture of the particle emission pattern in the momentum space. And this is nicely shown on this figure, and also of the figure is in the audience. Berus Kardan is our PhD student who nicely worked out this nice representation here. If you look at the projection of this flow components as a function of rapidity, you can see that at mid rapidity, which is shown in this insert with the black circles, the shape is almost elliptical, but it also changes to being more triangular when we move out from the mid rapidity. And this is characteristic for the forward, but also backward rapidities. Here, the triangular shape indicates that we do have interplay between the central fireball pressure and also interaction of the matter with the spectators, which are, as I said, present for a long time at these collision energies. Now data are there, and of course they attracted also attention from the theory point of view. And here I show you comparison of the V3 of the protons as a function of transverse momentum distribution, which turned to be more sensitive to the different types of the equation of states. Here I show you comparison to the transport model calculation URQMD. Paula Hillman is the one who made the calculations. And here you can see that this precision data could really nicely separate between the different choice of the equation of state, which are modeled in URQMD by means of the Skirm potential, and then by selecting different values of the alpha, beta, and also gamma parameters, one could then assign this equation of state to be of hard or soft character. And what authors of the paper said that our data prefer hard equation of state. So a little bit later, there was also a try to extract eta over S for HADES energies, again, based on the V1, V2 of the measured protons. What has been done here, authors have used so-called coarse-grained approach to extract this eta over S, because it is also clear that this observable is very much time-dependent. And here you see, for example, the error bars on this eta over S value is essentially defining also the time steps of the reaction. So in the earlier stage of the collisions, this eta over S is of the order of 0.5 and even smaller, like 0.4, which is also interesting then to connect this type of the observable with the, for example, electrical conductivities, which we also aim to extract from the Dilepton spectra, and more to this will come. So what is next to be done by using this data? So here work mainly organized with the colleagues from the SMASH, so group of Hanna Elfner. And here we try to use this high precision differential measurements, use also state-of-the-art dynamical models. In our case, as I mentioned, we will mainly focus now on the SMASH. And then we will try to use Bayesian multi-parameter technique in order to get the better constraint on the equation of state at higher density, but also including uncertainty on the symmetry energy. This part I did not discuss yet, but let me give you just prospects, because with HADES we did not contribute to this part yet. So symmetry energy and also slope of the symmetry energy, as you know, is quite essential for constraining the equation of state at high densities. It is very important, but it is also very uncertain, in particular when it comes to the high density regime. So what we know so far is the symmetry energy at the saturation density, which is also measured quite accurately at different facilities. And what would be essential is, of course, to predict or to shrink the spread between the symmetry energy constraint when it comes to the high density regime. How one can do that? One can do this by looking at the ratio of the charge pions that has been also identified as the good probe for this observable. One can also look to the flow of the pions as they come radiated from the heavy ion reaction. But what is also crucial for better constraint of the symmetry energy is also measurement of the neutron flow. And this is also something for future, because currently we are also discussing to extend the HADES spectrometer by the detectors that can also identify neutrons, and by this also provide the measurement for the neutron flow. So as I mentioned, flow of the pions are also essential to determine equation of state, but also symmetry energy. And let me spend a few slides on our data. On the V1, V2, and V3 component for the charge pions, this has been done for both charges, positively and negatively charged pions. What you can see here are the V1, V2, V3 for pi plus, with the black dots. HADES measurements are shown. Error bars are included. They are just so tiny that one cannot see them. Symbol size is bigger than the precision of data. And we also try to compare our data to the different model calculations. And as you can see, for the first two components, some models fit data better. And this model is the same one that also described V1, V2, V3 of the proton flow in the data. And you see that it seems that one reaches also better consistency between description of the azimuthal anisotropy, not only protons, but also of the pions. So, however, there are still rooms for improvements for different model calculations. And to give even more work to do and to compare to, we also look at the production of the pions and also their anisotropy in silver-silver reactions collected at 2.55 GeV. Here results are shown for 10 to 20 centrality class. Again, V1, V2, V3 measurements for the positively charged pion together with the model calculation. And also here you can see that URQMD model, which uses equation of state that describes the proton flow, fits the data best. And having all these parts together, we can only say now that by having flow measurements and also improved model calculations, having proper description of all the observables as a function of system size, as a function of centrality, but also as a function of energy, can also provide better constraint on the equation of state at these collision energies, again by means of transport model calculations. But let me now move on with the multiplicity of pions and also their spectra as detected and reconstructed by HADES in gold-gold reaction at 2.42 GeV. Here we look at the pion spectra transverse momentum distribution for negatively charged pions is shown here as an example. We look at the multiplicity dependence of the pions as a function of number of participating nuclei. We look at the pi minus, pi plus spectra, but also here I show you ratio, which is mainly related to the electromagnetic interactions, or Coulomb potential could be extracted from these measurements. And also we look at the angular distribution of the pions. Also here, we look at the comparison of our data to different model calculations. And here you can see also differences between the data to different models on every of these observables. And if we look, for example, at the transverse momentum distribution, it is not only about the yield of the pions itself, but it is also about different slope of the spectra, which is seen in the different model calculations, which is reflected, or the fact that pions produce these energies mainly due to decay of the delta, but also higher line resonances, and amount and also modeling of these resonances in different transport models realized in the different way. And this is also lead to the substantially different PT distribution of the pions as calculated in different models. How can we help maybe to contribute or to resolve this issue? We also look at the correlated pion-proton emission from the gold-gold reactions, 2.42 GeV. We have reconstructed invariant mass distribution for positively charged proton, pion and proton, but also for the pi minus proton channel. And of course, at the higher masses, this all spectra is dominated by many of the overlapping resonances, which have quite large widths. But what is still seen nicely are the peak structures shown here for different centrality bins at around mass of the delta resonance. And if we try to also describe distribution by the Breit-Wigner, we fail to do that, and one could clearly see that there is so-called kinematical mass shift of the deltas, and I will comment on this in a second. So we look at the multi-differential representation of this pion-proton correlated pairs. Here you see as an example for the rapidity distribution, but also transverse momentum for the different mass bins has been also reconstructed in this spectra. So how to understand this behavior of the mass of this correlated pi plus proton, pi minus proton pairs has been also addressed already in the 1990s by the colleagues who tried to explain PT spectra or MT spectra of charged pions by inclusion of the so-called S-matrix formalism. And here you can nicely see now pi minus spectra of HADES together with three different calculations for the pions which are emitted from the delta, depending on how the delta is modeled in the model. And here you can see that in order to describe the low transverse mass distribution of the pion, it is essential to include the proper description of the delta into the models, which is not yet the case for the transport model calculations. So this is something to be done. Data are there, and we hope that they will also help to constrain the model calculations in the better way. Another possibility to look at our spectra is to say, okay, there are many details in the microscopic transport models, but maybe we could be more successful if we look at description of our data with a few parameters only. And here, statistical hadronization models come to help with this. And I show you here examples of the model, which is extension of the terminator model to not boost invariant systems. And here you can see that with the few parameters, we achieved quite a good description of the transverse mass, but also rapidity distribution of different particles. And there are even better description in particular of the rapidity distribution of the pions, but also protons when one includes spheroidal expansion and the freeze-out geometry. And this work is in progress to come up. So it seems that our data could be described nicely by this approach. And not only if we look to the yields and spectra of particles, we can also look just at the yields. And here I show you another type of the statistical hadronization model together with the experimental data. Now for both ALICE measurements, and I think Johanna will discuss this in details in the upcoming seminar. But what is important to mention that indeed over the many orders of magnitude in the production of the different hadrons, which are essential either for LHC or also for HADES energies, because we also look at the quite rare particles. There is quite a good description of the particle yields achieved by means of statistical hadronization model. So here again, we go like factor of 1000 in the energy from ALICE to cis-18 energies. We go down with the temperature by approximately factor of 2 only. Of course, we change dramatically baryon-chemical-potential, which is now of the order of 800. And of course, important parts to mention here are the handling of the strangeness at this low collision energies, because here one has to take into account the canonical treatment for the strangeness at low beam energies, which is again realized by introducing of so-called strangeness correlation radius RC that has been used to describe gold-gold data. But what is also very essential is the inclusion of the feed down from the excited nuclei like helium-4, H4 and also lithium-4, as has been pointed out in 1988 already by authors, and very recently also by Edward Shuryak in the recent paper 2020. He pointed out about importance of the states. Indeed, only when one includes these states into the consideration, one can achieve reasonable agreement with respect of the number of degrees of freedom. So chi square over number of degrees of freedom are getting better when one includes these states into the consideration. Maybe one word to the canonical suppression of strangeness production. So here is the nice excitation function of the phi to k minus and phi to psi minus ratio, as has been now posted by Star collaboration on the archive. And here what is shown are only heavy systems. This phi to k minus ratio has been also intensively studied at cis-18 energies in the lighter systems by HADES and also FOPI collaborations. But what one can see is that indeed, when including this canonical suppression for the strangeness, one could describe the experimental observations quite well. Now more to the excitation functions of different observables. Let me spend 2 words on the lambda polarization at cis-18 energies. So until HADES data has been appearing on these excitation functions, there were still discussions on whether the maximum of the lambda polarization can be seen at around 1 or even 3 GeV collision energies. So now with the data from HADES for both gold-gold but also silver-silver collisions, we do show that polarization of the lambda grows as the collision energies. And let me emphasize on the one very important point that we know from STAR, but also from HADES measurements, as shown now in the top figure on the right side, lambda polarization has a very strong centrality dependence, which grows towards peripheral collisions, being in line with expectation for the larger orbital angular momentum in the more peripheral collisions. So therefore, when one plots the excitation function of the lambda polarization, one has to be very careful about centrality bins which are used for the comparison. So therefore, we also include open circles and squares on this point, which are shown in the closer centrality bin to the one which is measured by the STAR collaboration. And here one could nicely see now comparing this black star to the open symbol, which is gold measurement, that lambda polarization keep growing as a function of collision energy towards the smaller energies. So now with our silver data, there are also possibility to look at the lambda polarization as a function of transverse momentum and also rapidity distribution. And here, as well as for the STAR data, we do not see within our arrows any dependence on the PT or rapidity. And yes, so now we have possibility to study and also understand this observation by looking at the different collision system, different centralities, and also different system size. From the lambda polarization to the hypernuclei measurements at these 18 energies. So also at these 18 energies, we do observe hypertritons and hyper lambda 4 measurements where they are weak two-body decay channels. This is what has been done so far. Very clear peaks of hyperons has been identified, and statistics for both hypernuclei are sufficient to go for the multi-differential analysis and also lifetime measurements. And here, this last point on the compilation of different measurements from different collaborations also demonstrates that how our HADES measurements are in line with what has been observed by also other collaborations. So this is just a starting field and more to be done also in the direction of the hypernuclei measurements with HADES. From here on, I would like to move on to the more rare probe or more statistic-hungry measurements. Here we see, or we look at the system with the multi-particle correlations, and I keep here still with the question mark. So what we try to look at are the cumulants and also multi-particle correlators. It has been pointed out that the cumulants, they hold information about multi-particle correlators, and when investigating this CNs as a function of mean number of protons, one could also isolate relevant physics. Namely, if you look at the scaling of these observables and compare n, which is the order of the cumulants, with the scaling of these cumulants with the number of protons, you can actually say by looking at our measurements that alpha is approximately equal to the n, and this also has been stated to be a signature of long-range correlations or multi-particle correlations. And here there are many question marks, because if this is the case, then we have to understand from where this multi-particle clusters comes from. Maybe due to the stopping of the nucleons, you have many overlapping nucleons together, which is of course a very nice scenario. There are also early prediction of existence of exotic phases, but there are also model calculations that also say that we might see like a remnants of the nuclear liquid gas transition in our measurement. So to emphasize and validate all these question marks, we are currently trying to extend analysis to the silver-silver collisions at 2.55 GeV, but we also measured silver-silver collisions at 2.4 GeV, which could be more directly compared also to the gold-gold measurements. We also try to work towards better identification of our protons, or even better identification of our protons by means of identity method. And there are also quite some work is being put into the understanding of participant fluctuations. And here new ideas are coming from the fact that you can probably identify or get the better handle on the participant fluctuation in the data-driven way by employing event mixing techniques. And here we have expert on board. Anar is now actively working on all these bullet points. Another way to look at this question was that we create a system with multi-particle correlations is look at the centrality dependence of the production of strange particles in the gold-gold and silver-silver collisions. We have detected a variety of the particles, more easily produced lambdas, K0 short, K plus, but also more rare, K minus and phi. And here you can see that if one would try to fit the data with the common scaling parameter alpha, one gets to a quite good description of the data. And this may indeed indicate, so this universal scaling can indicate to the fact that in our system, strange quarks are easily reshuffled between the different hadron states. And to give you even like the prospects from the theory on this question, I show you here. Oh, okay. Work from a group of Weiser, Fukushima, and Koyo, 2020 publication, reference disappeared for some reason. So what authors say is that if the matter is compressed to the densities which are approximately 2 times of the normal nuclear matter density, one can discuss this matter, or one can discuss or talk about the quantum percolations of the interaction among the meson clouds. And in this case, if this is possible, then quarks can somewhat easier roam in the system. And this is even got the name of the soft deconfinement in this work. And this essentially would also support this picture of multi-particle correlations in cis-18 energy regime. To really validate this picture and to say that nucleon can be viewed as the quark core and also meson cloud, we did a dedicated measurement. Now for the detection of the E plus, E minus in the exclusive channel, we use pi minus beam, secondary pion beam, and we identify electron and positron together with the neutron in the final state. What you can see in our measurements, black dots are the measurements compared to the different model calculations, and just pay attention to this green and red curve. These two are view nucleon as the quark core and meson cloud, and you see that this model calculation describe our data very nicely. And another point to mention here, that the pion beam momentum has been selected such that we can study with details how exactly rho meson couples to the n-star 1520 resonance. We show that this is all ongoing via vector dominance model, and this is absolutely essential because vector meson dominance is the basis for the emissivity calculation of the QCD meta. And this, of course, has relevance not only for cis-18 energies, but up to the top LHC energies, because that's the part of the successful model calculations. So since I'm at the emissivity of nuclear matter at high temperatures and densities, I would like to discuss with you electromagnetic radiation. Electromagnetic radiation, real or virtual photons, they are important because they carry information from the source at high temperatures and densities. Without a strong final state interaction, photons can carry information about temperature densities of the system. And what has been established now over many years, that Dilepton spectra measured in the experiment can serve as spectrometer, chronometer, barometer, thermometer, polarimeter, and also amperemeter of the hot and dense system. I will discuss a few of them in the remaining minutes of the presentation. Let me start with the invariant mass distribution, which we have measured now for two different systems and two different energies. Our gold data at 2.42 GeV, as published already 2019, now has been extended by the Dilepton measurements at 2.55 and 2.4 GeV silver-silver reaction. And you see from the high quality of the data, we can now study centrality, system size, and also energy dependence of the thermal radiation seen in the data. How do we measure this thermal radiation? We have to first take care about electrons, positrons, which are radiated from the first chance nucleon-nucleon collisions, but also subtracting contributions to our spectrum from the freeze-out sources like pions, etas, and also omegas in the final state. And you can see that comparing our experimental data to this magenta curve, in both cases, you see a difference between the data and also cocktail calculations. And this is exactly what we call excess radiation. And we try to understand if it has thermal character or not. And we did this by comparison of our data to the so-called coarse grain transport calculations, which uses many heavy ion collisions simulated with the microscopic transport models. Then a system is separated in the small cubes of 1 femtometer size. And in every of these space-time cubes, we define properties like temperatures, densities, pion-chemical potentials, but also expansion velocity with which the system moves. And then by establishing the criteria for the system being in the local equilibrium, we can also involve in-medium spectral functions as computed either by many model theory, many body theories, model of Ralph and Jochen, but also calculations from the functional renormalization group or from the parity doublet model, as has been discussed in the recent papers indicated here. So if we compare our data to the model calculation obtained from these coarse grain transport models, you can see on the left-hand side that our data, so this is now excess yield of the dileptons compared to the in-medium spectral function of the rho meson, blue curve, matches very nicely experimental data, indicating that also at this small energies rho meson melts. We do not see any rho distribution at 770 MeV. This is also consistent with the conclusion made by various collaborations who measure dileptons at different collision energies. And we also can point out at this moment that this model calculation of spectral function of Rapp-Wambach describes the data measured at these different collision energies, guiding also our measurements or setting the good baseline to study also interesting physics when it comes to the excitation function of the Dilepton spectra. We can look now at this excess yield also in the silver-silver reactions and compare them to the gold-gold collisions. Now we pick up centrality bins such that we have comparable mean number of participating nuclei. So somewhat more central silver-silver collisions are compared to the more peripheral gold-gold reactions. And you see that data are found in the quite a good agreement with probably some trend of seeing more yield in the case of the gold-gold reactions, but we are currently finalizing our silver-silver data to be more conclusive on our statement with respect of the system and centrality dependence of the excess yield. We can also look at the momentum dependent of the Dilepton yield in silver-silver reactions. Here you can see 5 different momentum bins from the fast E plus E minus pairs shown with the blue to the more slow E plus E minus pairs shown with the red. And what we try to establish with this type of the analysis is to see if the omega, which has the higher momentum, decouples somehow from the hot and dense system. And here many things and many analyses are ongoing. First of all, to improve somewhat our precision of the measurement in this mass range, but also to compare our data to the different model calculations. We can also look at the transverse momentum distribution of the dileptons at the different mass bins of the dileptons. And this has been done for the gold-gold reactions. Here you can see slope parameter, which is extracted from the transverse momentum spectra of the dileptons as a function of dilepton invariant mass region. And here you can also fit this data with the fit. You can see that with this type of the fit, we can extract temperature which is as high as 70 MeV, 69 MeV, and expansion velocity of the order of 0.03. And this is to be compared to the kinetic temperature and also expansion velocity, which you can extract from the description of the hadron spectra, which is found to be 62 MeV and 0.34 for the expansion velocity. And this is very nicely fit to the fact and the picture which I try to indicate over here. Hadrons, they of course see flow which is developed at the freeze out, so the full 0.34 is seen for the expansion velocity as we see and measured with the hadrons, while for the dileptons you can see this value are very small, and this is related to the fact that our thermal dileptons are mainly radiated from the times of the collision where this radial expansion velocity is not yet fully established. And this is the nice result confirming radiation of the dileptons from the early stages of the reaction. To emphasize on this even further, we look at the azimuthal anisotropy of virtual photons. We look at this already earlier for gold-gold reaction at 2.42 GeV, but error bars were still large. And what we have tried to conclude with this measurement, by looking in the region of the dileptons below 120 MeV, which is mainly dominated by the decay of the pi 0 to E plus E minus and photon, we have seen this negative value of the V2, and we look at it as a function of centrality, also as a function of PT, and try to compare it to the measurements from the charge pions. And we have seen that in the small range of the dileptons, which are dominated by pi 0, measurement of the V2 is consistent with the charge pions, while when we move above the pi zero range, as a function of PT, you see that V2 is consistent with zero, but we still left it with the question mark. As I said, data are not of, suffering from the statistic, even this high statistic measurements. So now, Silva collisions at 2.5 GeV, flow measurements of the dileptons indicate a very similar behavior of the V2. We see the negative V2 for the region of the pi zero, which then turns to be consistent with zero towards the higher masses. And this is where we are currently working on to come with the more conclusive statement on this observable. We looked also at the helicity angle, because this also good observable for, say, if system is or photons are radiated from the thermalized source or not. If you look at the helicity angle in the virtual photon rest frame, you can connect them to the photon polarization. And we look at this observable again at the different invariant mass bins of the dileptons. And here you can see at the small masses, this very characteristic backward-forward anisotropy of our photons, which are consistent with the anisotropy for the charge pions. But then you see, moving to the higher invariant mass distribution, this polarization changes, is getting not as strong, and probably even changing its character when it goes towards the pole mass of the virtual photons, like rho meson. And this is very nice observation, which we also try to put in the context of our measurement in the neutron-proton collisions at the similar center of mass energies. Here you can see also this characteristic backward-forward anisotropy of polarization of the photons, and we associated it with the like delta-like contribution. So delta decays to the virtual photon and proton. But then if you move to the higher invariant mass distribution, this helicity angle even changes the B parameter to be negative, very similar to what we see now in the gold-gold reactions. And this has been pointed out in 1995 to be a hint that one switches like from the source of the dileptons, indicating that going towards the higher masses, one goes more in the regime where the vector mesons are decaying into the electron and positron. So this type of the analysis is being performed now for silver-silver collisions, and then we will try to make a solid conclusion from the both systems measured. Li Shuan, how well I'm doing in the time? I think I'm running out of the time.
I think it's okay. You can have another probably 5 to 10 minutes.
Okay, so this would be great, because then I can finish this discussion. What has been pointed out also already in 2006 by Guy Moore and collaborators, that by looking at the transport peak in the limit of the very low mass and the very low PT, one could also measure or get an access to the electrical conductivity. And this is again make a very nice opportunity to establish or measure this electric conductivity by measuring spectral function at very low masses and very low transverse momenta of the dileptons. And here more recent analysis has been done by Ralph Rapp, presented at this workshop. He again tried to look at the behavior of the spectral function of the rho meson at the different temperatures. And what he indicated is that probably the broadening of the transport, that the measuring of the transport peak might be quite difficult, but then if one measure very precisely spectral function of the rho meson at let's say not 0 cube 0, but at around 100, this could be already very important in order to establish this electrical conductivity for the system at the given temperature and the given densities. So this is a very nice, but also very challenging measurement. As you can imagine, one suffers at this very low mass and very low PT, not only by acceptance issues, but also by very strong contribution from the sources like Dalitz decay of pi zero and also further mesons. Nonetheless, experimentalists will take this challenge, and there are quite some discussion also to make this observable possible with the future experiment at LHC, like ALICE 3 experiment, which will be a very low mass experiment. But what we can also try to do, because we think it would be essential to study this electrical conductivity at very different temperatures, which would be very complementary to measurements at higher energies, is to look at the HADES data, which are already available. In the upper corner, you see our PT mass coverage of the dileptons. This is what, as I said, measured on the data, on the tape. What we try to do, we try to look at this distribution for the transverse momentum below 200, which is still too large transverse momentum cut. We have to move towards even smaller PT bin. And here on the left-hand side, you also can see our data and these big error bars, which you see on the experimental measurements, are mainly from the subtraction of the cocktail plus and minus from the pi zero decays, but also due to the correction of the spectra by the acceptance. And this is where we will spend now upcoming years, I think, to establish good quality of the thermal measurement, thermal dilepton measurements, also the very small masses and small PT. Last but not least, let me discuss about dileptons as chronometer, to put this also in the context of measurement of the possible phase transition. Dileptons has been established to be a good chronometer and discussed already in 1990s by collaborators as shown here. If one integrate the dilepton yield in the mass range of 300 to 700 MeV, and this particular mass bin has been selected in order to be more sensitive to the electromagnetic spectral function, but not to the temperature effects. And if one look to this mass bin and plot dileptons as a function of collision energy, one sees that there is quite a smooth behavior of this observable. And what would be nice is to see, of course, in the future, any possible deviation of smooth falling of this distribution. Why we would like to see deviation from this smooth distribution? Because in the case of the first order phase transition, one would expect that system lives longer because of the latent heat. And if system lives longer, it will also radiate more dileptons. Therefore, any deviation from the smooth behavior of this observable might indicate signatures of the first order phase transition or even critical endpoint. And what has been tried now is to, first of all, constrain the equation of state, but also try to include first order phase transition into the choice of the equation of state as discussed here. In this paper, recent paper from Moss, Strizzola, Steinheimer, there is a discussion of usage of the same self-consistent relativistic hydrodynamic calculations for simulating neutron-star merger events, but also to simulate heavy ion collisions. And authors has pointed out that indeed temperatures and densities which could be reached in the collisions of either neutron stars or heavy ion reactions are quite similar, and also entropy per baryon in both of the events are quite similar, which also allow us to well, look at one equation of state constrained by various observations to model our Dilepton spectra. So this has been done. Let me start from the lower panel. We use this equation of state, and we introduce into this equation of state also first order phase transition, and we try to see how many more dileptons will be radiated in this case. And we have seen that up to factor of 2, so more dileptons can be radiated in the case of the first order phase transition. Confirmation of this type of the behavior or amount of the extra dileptons that could be seen in the spectra comes also from the calculation done by the functional renormalization group. They try to also establish or calculate the amount of the dileptons close to the critical endpoint, but now not of the chiral phase transition, but still of the nuclear liquid phase transition. And also here one have seen a substantial increase of the dilepton yield in case one approaches a critical endpoint. And now new calculations are ongoing to also check this type of the behavior, but now for the true chiral transition to the deconfined type of the matter. And the very first hints I would like to present you here, this FRG functional renormalization group calculations are shown here with the dashed line. They are to be compared to the red dashed curve, and you see that for the mass above 1 GeV, there is a very nice consistency between the spectral functions. Once again pointing out that the dileptons at this mass range could serve as the very good thermometer, but then one still sees that some work is to be still done with the FRG group, and this is what is being done. And here we probably can also hear from in the future seminars from the FRG people to tell us about the prospects, also to have one equation of state with the consistent spectral function. And this, of course, would be the final aim of our comparisons of the data to the calculations, which are, as I said, have radiation of the dileptons and equation of state consistently done in the model. I will finish probably with this slide just to emphasize that we are currently preparing for the yet another beam time, which we hope will take place in 2023. We would like to do beam energy scan at CIS-18, go down with the collision energy down to 200 MeV energy. So 200, 400, 600, and 800 MeV will be studied. And here the measurements are mainly motivated by two main points. One is that we have seen by various models calculations that going to smaller collision energy, we will probe even more of the bulk matter as seen by in the binary neutron-star merger collisions. And on the other hand, we also would like to see what are the measurable consequences of phase transition and critical point in the QCD phase diagram. And here, what we will do, we will approach closer to the nuclear liquid gas phase transition, and we will try to see how all the relevant observables will change their behavior if we go from 1 GeV down to 200 MeV collision energies. And with this, I would like to stop my discussion. Thank you very much, and happy to discuss slides.
Thank you very much, Tetyana, for this very comprehensive presentation. So it's open to questions and comments. I do not see anyone in the chat window, but we do have a raising hand. So we have a Chairman call. Please go ahead.
Yeah, thanks a lot for the nice talk.
Thank you. Thank you.
Yeah, many questions, but just ask one first. If no more other questions, I'll continue. You mentioned in one of the slides that from V3 measurement, compare with the variety of models, and especially your QMD model, you claim the equation will stay stiff. And from the V3, yeah, that's right. And I would like to remind you whether it's due to stiffness of the equation state or the effect of momentum dependent of the mean field potentials. Mm-hmm. I think in the URQMD, there's no momentum dependence. At least for V1, we know if you use the momentum dependent interactions, then you can solve the equation state to describe the V1. And I don't know what's the effect of the momentum dependence of the potential on V3. So just to remind you, it's worthwhile to include momentum dependent in URQMD to redo the calculation to see whether the conclusion still holds.
Yeah, so thank you, Jiminko. I don't want to be taken wrong, so I just make the citata from a statement of the authors of this paper. You are absolutely right and correct. So momentum dependence is not introduced in the URQMD model, and as we also know from the older discussions that not momentum dependent hard equation of state seems to be identical to the momentum dependent soft equation of state. Okay, so that's the dilemma to be still resolved, I would say, but ideally we would probably move to maybe even more consistent equation of state and maybe beyond SCRM type of the potentials. But thank you very much for the comment. That's very essential.
Yeah,
yes.
I'm pretty sure you're aware of this. I just know maybe many people who are in high energy physics, they are not aware of this fact.
Yeah, okay. So it was absolutely essential comment. Thank you.
Thank you.
Thank you. The next question goes to Yan. Yan, can you go ahead?
Yes, if you can hear me, good.
Sure.
So actually, I have a comment to Jimin. So yes, you're right. So basically, URQMD does not include momentum dependence, and this study was done with the non-momentum dependent potentials. But the point actually we wanted to make was not about the hard or stiff equation of state, but the point we wanted to make is that actually this whole discussion about hard stiff in nowadays should not make any sense, because this is based on, as Tetyana said, this very simple SCRM potential where you have one parameter, free parameter, which is fixed at saturation density, which tells you then on your compressibility, while in reality, of course, we have other ways to determine what is the compressibility, and then we should have an equation of state which is fixed at saturation density, and then we should study what happens at higher density. So we have to go a little bit beyond this simple SCRM and then look what's happening at higher density. And the second thing I wanted to mention is that the V3, actually what we found does not contain any new information which is not already in the V1 or the V2. So to your question, yes, the effect on the V3 would be the same as you would see on the V1 or V2. So if your model can describe the V1 and the V2, it also works for the V3 and vice versa. That's all I wanted to say.
Thanks a lot. I'd like to know that. Yeah. Bilevel is study effect of EOS on V3. Thank you.
I mean, for this energy specifically, right? So for the hardest energy, it's basically the V3 is V1 times V2 some factor. Yeah.
Mm-hmm.
Thank you for the comment. Neil, go ahead.
Yeah, Tetyana, thank you for the nice talk, always. And I actually had a question on different slides, but on this one, on the right plot, two plot, I did not get your point. Do we have data from HADES on this plot about symmetry?
So we do not have yet HADES point on this plot, but we do have all the observables in our hands, which has been used so far to contribute with the points into this left figure. So like, for example, 4 pi data on the V1, V2 of the protons has been used to contribute also to this observable. But what we see now is that precision of the HADES data and also reach in the transverse momentum and rapidity is bigger, and precision of the data is better. We therefore have to see if we can also contribute to constrain the slope of the symmetry energy in the better way, but we do not have yet.
Okay, not yet. So now my question, I have 2 questions. I think one is on slide, I think it's 18, about the thermal fit. You compare a thermal fit one, and you see the right plot, what happened to, maybe too complicated to eta, but to lambda and K plus, also K minus. You see, they are not really consistent. Normally these particles should fit fine, right? Looks like something else is going on. Eta may be more complicated. So.
Yeah, maybe to eta, eta has been, let's say, always more complicated. We have seen this also in the previous measurements of HADES, consistently deviating from the statistical model, and also in the earlier days by the TAPS collaboration, it has been measured already that eta has been deviating from the statistical hadronization model. So here, to resolve this issue, there is a nice paper from Lorenz von Smekel and also Alexei Larionov. Paper is on the archive, where they try to establish following scenario. They say, first, eta couples very strongly to the resonance, which is n star 1535. Resonance n star 1535 is the chiral partner of the nucleon, and what they show, and we know from lattice-Kutzedy calculations, that at high temperatures but also densities, chiral partners start to move towards its ground state, which means that in the hot dense medium, n star 1535 changes its mass, and this also leads to the fact that you can more easily produce eta meson. So this type of the scenario goes in the direction that one probably will be able to describe eta. So now for the strangeness, I agree with you, there is something to be still done in the better way. For the RC or gamma S or whatever people like to.
RC only affect the phi meson, not really the strangeness, yeah, other ones. So.
Yeah, phi meson is anyway very interesting because it's strangeness neutral particle, and therefore it fits so nicely here. But one would need to take a closer look at this lambda kaon. I don't know if somebody would like to.
The next question, can I?
Yes, go ahead.
It's puzzling to me on slide, I believe it's 33, you slicing invariant mass, look at the transverse distribution, which is very nice, actually. I always think this is the way we should
this
analyze.
We know, no shoe. That's no shoe.
No, it's actually, I call time traveling, because the high mass would be a little bit earlier relatively. But I'm puzzled by this result. Do we expect we should expect a higher slope at a lower mass because they're from decays contributing from hadron decays, right?
So what we have here is what is been in the slices of the invariant mass are the thermal radiation. All the sources of the type of pi zero, eta, or anything else we know which contributes to the spectra has been subtracted. We look here only at the excess dileptons. So, okay, great. So the subtraction is done in the transverse direction, not in the integrated. Yes. Okay, then that's okay. Thank you. That's nice. Yeah. Okay. Thank you. Yeah, this will be nice compared, for example, with pions, this plot. For example. Yeah, thank you.
Thank you, Neil. The next one, Pion.
Yeah. Hi, Tetyana.
Hi.
I just had a question about your 3D representation of this azimuthal anisotropy, where you plotted also versus rapidity. So I was wondering how you do that, since the angles, so is it, yeah, since the angles between V3 and V2 are kind of random every event, right? So how do you, for the 3D plot, align the angles? Is this just for one given event, or how is it done?
So Berus, are you here? Maybe you switch on your camera and you can give all the details about this plot. I think we should give a chance to author of the plot to answer. Hi, Berus.
Hi, I unfortunately have no camera, so it's very easy to answer. In our energy regime, we do the measurement always aligned to the reaction plane. So all harmonics are measured to the event plane. And there is, or we didn't observe any fluctuation from different symmetry planes, as you mentioned. So all measurements are done with the same event plane. So, and then it's easy to plot them aligned in one.
Right,
3D
but isn't your
object.
V3 zero then?
At mid-rapidity, yes. But
I see.
if you
So
go
you get a
in forward and
finite
backwards,
V3
you
on
see.
average. Yeah,
And
I see.
As I said, it's the V1 times V2. It will actually give you then a V3. Sorry to interrupt.
Okay, that's interesting. Thank you. Got it.
Yeah, but the viscous attenuation for V3 and V2 are not the same. So technically, you know, the anisotropy that you see is not the original anisotropy.
What is the original anisotropy with respect to the reaction plane then?
But
right? I mean, you're thinking again in terms of fluctuations, but that's not the source here. Because you always have this.
What I'm saying is, well, what is it that you're trying to tell me with this plot?
The one to the right, Roy?
Yes.
Well, it's mainly I think this one insert is probably the message to get out. That's the mid rapidity versus forward rapidity, and there you can just see what happens to the source if you move away from the mid rapidity. You see what happens to the matter, which is squeezed by the two spectators.
Yeah, but what I'm trying to say here is that when you move forward and backwards of mid-rapidity, you change the multiplicity density. So that's, in my language, that's saying that you change the dimensionless size of the system, which means that you also influence the viscous attenuation as you move forward and backward. Mm-hmm. So you can show me what looks like an effective anisotropy, but I'm not quite sure what it means.
Mm-hmm. Okay, so maybe one could just plot this, by means of models, just to check what you just said, right?
Yeah. If it's included in the model, right? So you would need some kind of a 3D type model as opposed to, you know. Yeah.
Okay. Thank you, Roy, for the comments. Zhao Chen, please go ahead.
And then a very nice presentation. Actually, I have a question about the statistical fitting to the HADES data to extract the result temperature and the corresponding μB. I noticed that in last year and the 1 year before, there are two set of numbers for the μB and the temperatures expected from this. I just want to listen to your comments.
Okay, so my comments is following. We have many more than just two sets of these temperatures and chemical potentials, because there are so many knobs one can pull up, down. So we try to include strangeness to the fit. We try to not take care of the strangeness. So there are many things. What we are now trying to do is to look not only at the particle multiplicities, but also at the spectra of the particles, because we think this is kind of essential of doing that. And yeah, also here we are not yet at the set of temperatures and chemical potentials that we can uniquely identify for this collision energy. So I'm sorry to maybe disappoint you a little bit, but there are still many, you know, little particles, but many parameters. So you run in the problem, you have as many parameters as you have particles. So this is not very advantageable with all the strangeness, correlation radius, and many other things. So I don't know, we now believe that this Terminator 2 or even Terminator 3 version of the model, which is being currently somehow summarized, might be the best one to use, because you will get temperature, chemical potential, looking not only at the yields, but also the spectra of the particles. And
honestly, one interesting solution is that there are one solution, it gives you the temperature around 70 MeV, which is actually close to the temperature extraction from your measured Dilepton environmental mass. That is actually catch my eyes, because
okay, so let me comment on this 70 MeV. If you have ever seen this number, not on my slides, because that's a very obvious, like a counterproductive thing. If you have 72 MeV Dileptons penetrating probes and you have 72 MeV for the chemical freeze out, then something is okay, with the question mark, I would say. So if you look in the details to the presentation where you have seen these numbers, 72 MeV and also chemical potentials that has been extracted there, and then you try to identify at which density your system is frozen out, this number also turned out to be unrealistic, and therefore we just stopped coming up with yet another set of the data and decided to make our homework first, and then show the consistent number for the temperature chemical potential, which is also supported by whatever, looking at the density at which temperature is, at which system is frozen out, looking at expansion velocity, for example, of the system, right? It cannot be also that our expansion velocity will turn out to be comparable to the RHIC, top RHIC or LHC energies, right? So this many things are still to be on the table and to answer.
Okay, thank you.
Thank you, Zhao Chen. Next, Jiang Yong.
Yeah, Tetyana, very good talk. I want to go back to the earlier discussion on the flow, like slide 11. So what is to be measured here is just the rapidity odd V1, right? And the V in odd basically you measure the, it's a rapidity odd component of the flow, because maybe the way that was done is that you use a spectator, and like the way how you define the event plane basically is only the odd component. But there should be a rapidity even V1, V3, right? Those are so-called dipolar. For example, V3 you have this type, you have a dipole for the V1, you have a triangular fluctuation for the V3. So Yang said that this component should be very small, but actually, have you checked that and how big this rapidity even component should be?
Okay, so I am not aware. Beros, maybe part of your PhD you have that. I need to call my friend Beros.
I'll make a comment, right? I mean, it has to be small. I mean, look at the viscous, look at the effective 8/s. that is extracted from the results. If you go back to that, it's about a factor of 8.
I'm asking an experimental question. Is a way to check it and actually measure this, because you can determine the participant plane, not very forward, but
yeah, well, we tried to measure it at EOS, and it was negligibly small.
How negligible?
Well, I mean, within the statistical errors that we could measure, we couldn't tell if there was anything.
I see, but HADES have much better statistical error. Error bar is negligible here.
Yeah,
so,
but it is small. They even.
Yeah, I would say it would be nice to be able to see that, and then you see, okay, the signal is smaller than this, because this actually tell you, as you say, the viscous damping and also the fluctuation may be different from a high energy.
Yeah. So here something has been done to look at the eccentricities, but I really do not have now a picture in my mind to describe to you. Berus, would you like to take this one, or to-do list, or answer already?
As far as I know, we didn't observe it in a significant amount. So it was the topic of my PhD thesis, and then we dropped it to do the reference measurement, which is shown here. So the odd one, which is shown here with high statistic and in a multi-differential way. But it was original the topic of my PhD thesis, which changed to this. So I cannot confirm that we see something which is significant. So the
okay, so but the question is, how significant is significant? And I think we can just go back and check this. So no answer at this stage. Negligible or non-significant, we can hopefully also justify.
Yeah, because the reason, because just from global model, there is a quite large event by event fluctuation, right? Basically, what is measured here basically have no fluctuation, right? Everything is averaged out in a sense, but there is just from the picture of global model, there should be a large event by event fluctuation. Maybe they do not survive, but
this is a beam energy of 2.4 JeV.
Yeah, but there still be a large event by event fluctuation on the eccentricity level.
You know, at these beam energies, it's not even clear if Glauber makes sense, right?
Yeah, but I think we can. I mean, we just make a claim that there's no fluctuation at all. I mean, I think that's very interesting.
There's fluctuations, but if the viscosity is large because you're largely in the hadronic phase, then it basically dampens out.
Yeah, but I'm asking the experimentalist to give us answer. So,
Jiang Yong, I think you make your comment, and as Tetyana said, they will follow up, but they cannot provide answer today. Do you have other questions, Jiang Yong?
No, that's the only one. Yeah.
Okay, thank you. Zhao Chen, you have another question, I guess, right? Go ahead.
Yeah. Tetyana, can I go to the connectivity slide?
But let me go to the acceptance plot, because we do not have yet conductivity. This is a long way. So let me show this one.
Yeah. For this one, if we I'm just thinking experimentally, how do we if we overcome all the difficulties to remove the background and we get the acceptance to measure this, how do we extract the connectivity based on the enhancement?
Well, you basically look where this line crosses y-axis, and then you read it off from the measurement, from the y-axis of your measurement. Okay, so that's the fantastic vault, but I think this challenge we should take, because it's in a sense in experimental way defined observable, not so you measure this assuming we overcome all the precisions, and let's say a solid red curve is our measurement. Then you just look at the y-axis and you say what is the electrical conductivity.
So that is the signal, right? But how do we get the connectivity values from that?
Yeah, this is exactly what is written over here. So this little formula tells you spectral function. This is what you measure, or we try to measure in the limit of 0 temperature, 0 PT, 0 invariant mass. And on this left-hand side, you see sigma electric, which is electrical conductivity. So I think that's the plan.
Okay, thank you.
And this parameter, you know, I mean, electric charge.
Thank you, Zhao Chen. Any other questions, comments from the audience?
Chairman, can I just make
Yes,
a comment?
Yeah, Chairman, please go ahead.
Yeah, regarding your measurement of pions at 2.4 GeV or so, and you said you showed all the theoretical calculation, they failed to reproduce the data, the total yield, D and dy. Oh yeah, here, the figure, second figure from the left. And I just remind you, we recently wrote a paper by including artificially a parameter to reduce the angled and delta cross sections. Then you can bring all the curve down. In all those theoretical models, they treat the and as the free cross sections without any median effect. And we already know in heavy-ion collision at this energy, there are median effect. Of course, very hard theoretically to calculate the median cross sections. So we just use the parameters and reduce the end and delta cross section. Then you can bring that theoretical model predictions with your measurements. Just appeared in fixed letter B recently. I don't know if you're aware of that paper or not.
Not yet, but I will definitely take a look at this paper, which goes a little bit more in line with this type of the measurements. So I don't know if there is the chance then to just use the model and try to describe our pion proton experimental data. But you say just on the cross section, reducing delta.
Yeah, the cross section. There's a cross section.
So this is not gonna do.
Yeah, because we know in the lower energy heavy-ion at this energies, we need median cross section for elastic cross sections. If one is a free cross section, one will not reproduce many things. One need median cross. As you go lower in energy, the larger the median effect, because of Pauli principle, right? And not on the final state, also in the intermediate states, because in calculating all those cross sections, you have to calculate T matrix. Once you calculate T matrix, including the Pauli effect in the intermediate states. Therefore, for a very baryon dense matter at this collision energies, to get there are a lot of immediate Pauli effect, not only immediate, also the propagate also the median effect that normally reduces this end and elastic cross section, also end and delta elastic cross sections. Unfortunately, there are now systematic study of those immediate effects. So generally in heavy-ion community at the low energy, they just treat as the parameters. And delta cross section, we treat as a parameter reduced by some factors. Similarly for end and end cross section, reduced by some factors. One needs those cross section to get many things corrected. For them, the famous balance energy, the low energy heavy-ion condition, well, the directed flow vanished. One needs an immediate cross section or a huge suppression and elastic cross section to reduce the balance, where the balance energy occurs. So that's a well-known phenomenon in low energy heavy-ion collisions. But in theoretical activity has not followed up with this phenomenological approach. I just remind you, may indicate the need of including an end-to-end delta in median cross-section to explain the deviation between those model prediction of a pion multiplicity versus what you have measured by HADES.
Yes, very good. We will take a look at the paper, but also we'll try to run the model and compare it just to the experimental data. I think model is available, right?
Yeah, that we did. That is, you can see our paper. We go through more or less your data, those 4 points. We also show D and dy, also the PT spectrum. PT is a little bit trickier because we don't have the pion potential in the codes because the pi minus, pi plus have a different optimal potentials. So you really to understand the PT spectrum, pi plus, pi minus, one not only need the Coulomb potential and also need the pion potential. And very few codes, including the pion potential in the calculations. So that we are planning to do in the future as well.
Okay, thank you, Chairman. I have a question from chat from Soman. If I'm sorry if I pronounce your name wrong. Can you just go ahead to ask the question?
Okay, thank you. So I actually missed the first part of the presentation, so I'm not sure about the slide. What is the motivation of slide 15? But I was saying it shows that PT spectra is not explained by various models. What about the Salis distribution function? It seems to work very well even for the low PT and high PT. So could that be used to study of this one? I'm not sure about the motivation. I'm just making a comment that PT spectra can be explained using Salis distribution function.
Maybe I lost the question. It was about high
I want to know the motivation of this slide. Slide 15.
Yeah.
Yeah, the PT spectra is shown to like different models are used to explain the PT spectra, and all seems to not working very well. So I was saying
so what
that,
what we try to do for this particular spectra, and this can be found also in the paper, for every curve you take, for example, let's say SMASH or IQMD model, and you can also plot cocktail of the resonances which contribute to this spectrum. So you can identify was a pion comes from delta, was a pion comes from N1520 decay, was it comes from delta higher mass 1680 and so on. And this we try to do, and we have seen that PT spectra of pions which are radiated by different resonances, first of all, sometimes have different shape, but also often have a different height. And this goes back to what Jim and Co discussed. I think it's not only about delta or NN goes to N delta, it is relevant for every resonance that can be excited in this hot and dense matter, because they all suffer from the same physics, right? Short-lived, broad resonances, and okay, I don't know. I cannot do more as an experimentalist to measure spectra, and I leave it to discuss for theory. Yeah.
Okay, thank you, Tetyana. I do not see any further hands. Can I ask a last question? For the Dilepton V2 and the polarization, are those results sort of cocktail, subtracted, or inclusive?
So for the V2, what we have seen today on the slides, these are inclusive E plus, E minus. So what we will try to do, but this is not so trivial because you need to learn and to measure first V2 of eta, for example, before you come up with the V2 of the thermal radiation. For silver-silver reaction, you have to know what is the V2 of the eta, and this has not been measured whatsoever by anybody else, and this could be a topic of many years to establish the flow of the eta. One could make an assumption and say that flow of the eta is of the same order as pion, because they might have similar origin, but one would still need to take this more into discussion. In gold-gold reactions, for the higher masses, we are more sensitive to the thermal yield. Contribution from eta is just on the level of 5 to 10%. And therefore, even if eta contributes with the V2, it would be very little. This is not any longer if you go to the higher energies, and this we still have to do. Same true for the polarization angle. What we have seen today are inclusive E plus E minus signal.
Okay, thank you, Tetyana. I see one comment by Ulrich. Would you like to make the comments, or you just leave to Tetyana to have a look?
Not really. I just wanted to point out that I mean, for the number of pions, two things come into play. One is the production of the pions, and this you can suppress by depressing the delta excitation. And then in addition, of course, there's pion reabsorption. And all I wanted to point out is one has to be careful that these two processes are treated consistently, because they are essentially connected by time reversal invariance. And I mean, people in the various transport codes do this consistency requirement with various degrees of freedom, you know, and one has to be careful on that. That's all I wanted to say on that. On the other hand, I mean, this overestimate there is really not a new problem. This I also wanted to point out. I mean, already 20 years ago, we wrote a paper saying that this is a problem for the pion data, even for 4P. 4P, it was not that big the discrepancy, but this is an outstanding problem. And indeed, what Chemin mentioned, the suppression of the delta degree of freedom, this was already worked on at that time with various degrees of freedom. And sometimes it's just a parameterization. Sometimes there is an actual theory behind it. And as far as I'm aware of, the best one is due to Alexei Larionov, published about 20 years ago on that. And he has the most theoretical model, so to say. And it would be nice to look at that again in view of these data here. Okay, thanks. That was all.
Okay.
Can I comment just so? Can I just say a word?
Maybe just you say a word. Yeah.
Yes. Sorry, Ulrich, I forgot to mention you. Yes, Ulrich and his postdoc that time 20 years ago did one calculation based on one boson change model to study the E-median effect on angled and delta cross sections. Of course, once you know the angle and delta, then you can and delta and by the detailed balance. So I appreciate Ulrich's comments. So in our paper, we didn't use those theoretical E-median cross sections because the reason we tried didn't work. So we have to suppress more than predict the pion production based on theoretical predicted E-median cross sections. Right? It's tough to do calculation based on everything microscopically. Sometimes to fit the data, you have to into the phenomenological factors. Unfortunately, that's the way normal transport model works. If it was started from first principle, calculate the E-median cross section for elastic and inelastic and all the microscopic optical potentials, it's very hard to reproduce data. Unfortunately, that's the stage of transport model.
Okay, thank you. I think now let's thank Tetyana one more time for this beautiful talk.
Yes, thank you. And maybe before you thank me, I also would like to use the opportunity to give my thank you back to you, because times are hard, as you know. And I know how much you, your families, and also your countries are doing to support my country, which is currently in danger. And I only would like to express my deep thankful for all the support you do also on the scientific side to take care of students and senior scientists. So thank you.
Thank you, Tetyana. I think then let's end today's seminar. Xiaofeng, unless you wanted to say a few words.
No, I just want to thank you the very nice presentation that Tetyana made, and also thank for chair the seminar. Yeah, thank you everyone for participating.
Okay, thank you.
Bye. Goodbye.
Bye.
See you soon.
See you soon. No, yes. Have a good flight.
See you. Yeah.
There was 118 participants.